Sandy Munro dropped another video of him walking the Tesla factory floor with Lars, Moravy, Tesla's vice president of vehicle engineering, as they showed off how the stainless steel for the Cybertruck, or as Tesla likes to call it, HFS, hard freaking stainless steel, is stamped and bent. Today, we're going to highlight some of the most amazing and interesting parts of this video. So many ways Tesla is able to innovate and eliminate steps. And the best person we can have joining us today is Jeff Lutz. He knows about factories and he knows how manufacturing and supplies are put together to reduce costs. Welcome, Jeff.
Hey, Herbert. Great to be here. It's a fun video.
We love it when Sandy releases these videos, and this is the first time we get to see inside the factory. We're going to watch some of the clips and you're going to react to them. The first one is this about material utilization. Let's watch this.
We're about 80% utilization on the panel.
That's amazingly high.
Well, they're pretty square panels.
Yeah.
So they're kind of easy to nest.
Yeah, well, I guess so, yeah.
Yeah, it's usually 60, 70, right? But
well, around 45.
Okay,
45,
if you're
50.
bad at what you do, sure. But
Yeah.
like we
What?
try to, if you're bad, maybe 45, but we try really
no,
hard.
it's on average, that's about, because I look at things in entirety. Now, you're looking
sure.
at the stainless, I'm looking at
Yeah, if you look at the whole
even
vehicle.
the whole vehicle plus the crap that comes from some supplier or something.
Yeah.
Jeff?
Yeah, so let's, what I hope to do in this video is really pick out a couple of key concepts and up-level and kind of what it means in a broader context. I could sit here and geek out about, every little detail in the video, and I've watched this video a couple of times already, but the key here is to up-level it. So that utilization comment, you've heard me talk about utilization in the framework of a factory and in the framework of the supply base in terms of the utilization of their fixed capital. What Lars is talking about here is the actual utilization of the blank stock, of the actual material on a roll. And what he's saying here is basically, as that material is unwound and used throughout the process, they're getting roughly 80% utilization of it, and the rest of that, is material is being cut out and put to the side. So what Sandy was saying is he was accustomed to seeing that in the area of 45, 50%, and then he was trying to couch it in terms of the entire vehicle and small parts and so forth. But in general, from a material utilization and efficiency perspective, what this means for the Cybertruck is it means that they're throwing less material away. And so when you can keep that conversion rate that high, that's great from a COGS perspective. That's great from a sustainability perspective. And it's probably industry leading if they can get that well above, 80%. And part of that has to do with the shape of the vehicle, I believe, as well. That really helps. So this is now material. This is raw material utilization. That high utilization is a really good sign. I'd love to know what the rolled yields are through the whole process. So I don't know what Lars was referring to in terms of that point of utilization. But if you were to assume that that's how much utilization they're getting from raw stock into completed vehicle, that's a really, really good thing for Cybertruck COGS.
So this is the first of its kind laser blanking line. What it does is it takes coils, it unwinds them, and it's taking out the internal stresses from the raw material. It's passing them through something called a leveler. All it's really doing is it's got a bunch of work rolls and they're moving up and down, and they're flattening the part. We want to be careful that we don't work the material too much, because you do something called work hardening, and then you shear the part later on.
Yeah.
So this was a special development as well. This is something that's primarily used in mills. So we actually source it for a blanking line.
I love that to actually finally see the steel rolling through.
Yeah, and there's a couple of companies that make those machines. And so I'm assuming Tesla partnered with somebody. Now, the key is a couple of things that came out of that video. One was they talked a little bit about process controls of the material and what they can and can't do. And that's a theme you'll probably hear throughout the video. And that's really important, that Tesla knows those process parameters of what they can and can't do. So basically what you're trying to do with process control parameters is through every stage of the process, you're trying to figure out what the upper and lower boundaries of what you need to do to that part to get it from, point zero in the factory, coming inbound to a complete product. What are the things that you can do from a process control perspective to get to a final part with the highest rolled yield? And the rolled yield means losing the least amount of material throughout every stage of the process. So he talked a little bit about process controls and not overworking the material, because that would impact rigidity, ductility later on in the process. And I think they're going to talk a little bit about some of the controls in terms of process variation, dimensional process variation on the part in a minute. And one of the other takeaways is I believe a lot of this machinery is really meant for, somewhere on the order of like 1 millimeter in terms of accuracy, 1,000 microns. And I think Tesla is really trying to get this down, well below 100, maybe, below 50, below 30. I think we'll hear some numbers a little bit later in the video. So Tesla's trying to take something that's out there on the market and improve process controls, working with the supplier, get it, this is physically installed. The other thing is he says, you normally see this in a mill. This is physically installed, co-located in the Tesla factory. So fastest point of defect detection, defect resolution. You're not making a problem at another supplier, putting it on a truck or a train, and then shipping it over and then finding it 4 days later. They've got real-time feedback and everything, which is great.
I know, but I'd rather have you say it. What's the thickness of the material?
So we have two thicknesses. Our doors are 1.8 millimeters thick, and all the other parts, like the sails, the hoods, are 1.4 millimeters thick.
1.4.
Correct.
And we worked hard to get that strength up on the stainless, because the original we were about 2.53, but we actually increased the strength of the HFS over time. So we're able to get, while doing that with the ductility for forming, we're able to still get that strength and bulletproof toughness.
Yeah.
With having a thinner material.
Cool.
Correct. So this is actually designed for 3 millimeter, but it's good that we're not using it.
That's where we started.
Yeah, correct.
Yeah. So that one, what you're trying to do with raw material in this situation is you're trying to minimize thickness as best you can. Obviously, that would minimize the mass of the material that you're purchasing. And so Tesla obviously started a lot higher, somewhere in the 2.5 to 3 millimeter range. And what they realized is that there's certain parts of the vehicle that they can get down to 1.4. And then I think the trade-off, the key trade-off was side load performance. And then, probably a secondary thing was the whole thing about having the doors be bulletproof. So the doors are, looks like they're a little bit thicker at 1.8. So there's two different thicknesses that they're using of the material that presents some complexity. That's not, perfect. That's not a panacea. That's not a great thing. Over time, I think they would want to get that to be one thickness if they can, but I'm sure they've explored it, and this is where they're at today. I'm trying to think, is there anything else? No, I think that's a pretty good overview. So two different thicknesses of materials, what we learned at this point. The other thing that they're battling with is you can't get too thick, because then you'll lose that ductility, that ability to bend and form the material in the factory without it having orange peel and cracking on the outer layer. So that's the other. So there's all these different trade-offs. If you're Lars, if you put yourself in Lars's hard hat for a minute, he's got to perform in the reliability lab. He's got to get the mass, so he's not utilizing too much energy from the battery. And then he's got to get the cost down, so he wants to reduce the amount of raw material. He's got to yield it through the factory, so he's got to make sure it's got the right ductility. And then he's working with Charles Coleman's team, who's doing the material engineering for Tesla and SpaceX. And that's where the real innovation is. This is Tesla's own material coming in. They're not just buying some off-the-shelf roll of steel. This is Tesla's purposefully engineered material. So what I'm gathering here is Tesla was able to probably get this material. If this was off-the-shelf material, it would have had to have been much thicker, which means they would have used more material, more mass, less efficiency in terms of the battery and battery performance, and they would have had a tough time, manufacturing it in the factory. So I think the big innovation here is what they were actually to be able to develop with that HFS metallurgy. That's the key that unlocked everything else.
It's a real miracle, like you were saying, because he has to build something that works well for the consumer, the vehicle, but also has to work well for the manufacturing of it. they had to invent their own steel to do this, but they found that, needle in the thread the needle.
Shows a good overview of the line. So you have the uncoiler, as I explained, where the actual raw material, we call that a coil, is being loaded. It's being unwound as we speak. It's going through the leveler or straightener, depending on what you want to call it. Then it's going into the laser booth, which is what you see right over there. It's airtight, light tight because of emissions and whatnot. And these are two lasers working in tandem. And right now what's being cut is the hood for the Cybertruck. It cuts up to 30 microns, and it's the first laser of its kind to do that. Typically, these machines cut at 1 millimeter. This was a special development with Tesla and Schuler.
Yeah, so Schuler, looks like Schuler did that whole, the whole operation there, including working with the laser cutter. I don't know if they're using Trump, or there's other different types of laser vendors. I think we'll see that later in the video, so that you heard them, that there's a special development for Tesla in terms of accuracy. I think that's the key takeaway there. The other thing is everything's got a camera on it, and that's really for kind of supervising and kind of watching what's happening and trying to debug things real time. But I would I'd venture to guess that every one of these pieces of equipment has a more detailed camera and a set of optics and light for doing some real time measurements as well.
Love it. It's all high tech here.
Yeah, together. Correct. So overhead conveyor belts, parts actually come
And then
through.
come see it drops one.
Yeah.
And we just stack them up. It's very important the only thing that really can scratch HFS is HFS.
That's right.
So we got to be careful when we put it down that we're not
Yeah.
rubbing
Right.
it against each other.
Yeah. That's one of the other things that most companies will have the stuff coated. It'll have a plastic film, and you don't.
No, correct.
So this is kind of big stuff all by itself.
Correct.
Yeah, so these are the different blanks, yeah?
Yep, different
Yeah.
blanks, all within accuracy. Tailgate, fascia, hood, doors. Forgot
Excellent.
about that for a second. And then we have a measurement system.
Yeah.
So we're producing hoods. So typically we have a periodic quality check. So we'll take the part, put it on here. It's just a nice fancy 2D light scanner.
Yeah.
And what it does is it compares the cat that we're
Right.
cutting to in relation to what we're actually
Wow.
Yeah.
measuring.
So it's like a giant optical
Yep.
comparator.
So just watch your eyes, everyone.
Yeah, it's going to turn on.
yeah.
Takes a picture. Hopefully my arm didn't get in the way.
No, dude.
No. Well,
You can even sit on it and it'll be fine.
yeah.
all the points.
Yeah, so all the points are within spec. That's what this is measuring the outer contour.
So you
And
can
it's
see this
checking.
level of micron precision here. Elon's been pushing us
Yeah.
on. You can see some of these 7 microns, 15 microns, 26, 2, 26. These are pretty intense levels of
Yeah.
precision.
Yeah.
Correct. And we got to be careful because we're doing periodic checks to make sure this machine has a good CP or CPK, or repeatability is what we call
Yeah.
it.
CPK.
So that's what
Yeah.
Elon was referring to as micron precision, and they've got it. They did it. It's happening.
Well, yeah. I mean, if you look around that part, there's probably 30 or 40 different points that they're measuring. And you heard that gentleman talk about process CPKs. And that's really a measurement. That's an equation to understand how well centered and how consistent are each of those readings. So each of their readings probably have their own individual CPKs that they're monitoring. So when you're looking at process capability, you're trying to understand where the process variation then therefore comes from. Is it coming from the part or the raw material itself, or is it coming from the machine that's actually processing it? And what these engineers can do is they can look at the data, and they can also run some kind of between shift tests that they can run to basically understand the process capability of each machine, before they turn it on and start putting live production through it. So there's a series of checks that all this equipment has to go through. And I would venture to guess, so a couple of things I saw in that video. One is, they're stacking parts right on top of each other. He said the only thing that can scratch HFS is HFS. I'm hoping that this works out, and I'm hoping they don't need to actually procure, film liners or anything like that, because that's just added cost, and all of that is scrap and all of it's waste. You put that on in the factory and you take it off. So they're trying to minimize doing that. I hope it's probably working okay at low speeds. I hope it works okay at some of the higher speeds as well. and you don't have a lot of scrap. Scrap of the actual stainless would be one of the more costly things that they could have. And so yeah, I'm trying to think, is there anything else? So yeah, they've got the measurement capability right there on the spot. And the other thing with that hood, that's a pretty complex thing to measure because it's got a curvature on one side of that. So that light box and comparing it to, and that was a 2D a two-dimensional measurement. That's probably the best you can do in that factory environment. So and that's how they make sure that everything that's coming out is is to spec and can be passed on to the next stage. And that's what's key. You don't want to pass bad material to the next stage. What I would be interesting to see, we don't get to it in this video, is I would love to see the operation of, that raw material coming off of each one of those pallets and seeing it all kind of mated together into a truck. Like, I'm wondering if they're doing any other kind of optical sorting between those parts being completed and the truck being assembled to make sure, like, okay, I've got this outer door panel, I've got this inner, do these, is there any kind of binning, or is this all, being made, to spec and just coming right off the line? That would be interesting to know, but we can keep going through it.
Wonderful clip. Micron precision, and then HFS. The only steel that can scratch the steel is HFS.
As you can see with all the equipment, we're ready to roll at like high volume. Now it's just like, how do we ramp, go slow, get quality right.
Yeah.
Yeah, I put that clip in for a reason. That's about halfway in. There's other stuff that we can, we'll go through, Herbert. But what it looks like is, it looks like exactly what they described, which was they've installed, somewhere on the order, not every station's going to be equivalent, but this 125K annualized capacity. And it looks like from hearing some of the other supervisors and managers speak, it sounds like that there's more equipment coming in. But in terms of a very large operation, like they've installed and they have the product, one of the big milestones of getting a product into production, which you would hate to see, by the way, if you're watching one of these videos, is a bunch of people kind of manually wrapping on these parts or doing a bunch of stuff, like, because the production operation isn't ready to go. And it looks like there is a full end-to-end production operation to do all of the stainless up and running. And I know it sounds like, well, okay, that's great, Captain Obvious, but in many cases, sometimes companies start at low speeds and their production operation isn't working the way they want, even at the low speeds, and then they take it and they do something manual in the meantime. And it looks like that they've really got everything in place. And as Lars said, that they basically turn the dial to the left and they start at low speeds and try to get really focus on the quality side of the equation. So when you're ramping a factory, you've got these two knobs, and you're basically you're trying to turn the volume and the speed up to the right. So you're putting more material in, you're running the machines at a little bit faster rate, and then you've got the quality lever on the other side of it. Kind of think of it as an accelerator brake analogy. And on the quality side, you're trying to make sure that you're not losing more material through the process, because that'll take your scrap costs up, that'll take your overall vehicle costs up, and you're not causing a bunch of quality defects that are going to slow you down or cause a reliability or upstream issue as you pass that material. So that's the stage that it looks like they're in now. They've got all the production operations, and they'll bring in more in terms of volume and quantity and replicating what they have. But it looks like they have everything there to make the truck using all production tooling, which is a great sign.
I think also very, very efficient. We might get more production than we're thinking about or expecting. First of all, thank you so much, Jeff. You need to be following Jeff on X. This is brilliant. We're so lucky to have somebody with your expertise walking us and interpreting what we're seeing. So for this next clip, I'm going to go play it at a 1.25% speed. You just tell me when to stop, and then let's watch this together.
Yeah, there's a view of the press from the side.
Should open up. Yep, now it's opening up. And you'll see that's the fully formed door ring that I was talking about. Are you doing inners or outers right now?
Right now we're doing inners, inner left.
Thanks.
Here's what they look like when they're done. This is a body side inner.
Check for heat.
It's gonna be a little hot. It might be a little hot.
No,
It's
it's
too bad.
not even warm.
Now,
This
just
will
so
cool
you
down
know,
fast.
we're actually going to unload this with a robot. We have what's called an automatic, basically using a robot to automatic racking system.
Yeah.
So
Yeah.
they're going to automatically get put in these racks, and we're going to take them off the forklifts. Right now, we're not 100% ready to do that yet.
And they go up this conveyor, right? Well, not as these parts, all the parts. They'll go up here, and we'll go up there, and we'll show you how we form the stainless from
Yeah,
there.
so boom, we got our lift right up there. We supply body shop, which is right over there.
Cool.
Can we pause it there, Herbert? Yeah. So
I was going to pause
right
it
now,
myself
the-
because, first of all, they're using multiple layers, the vertical, not just the flat, and then they're going to add more robots. Yeah.
Yeah. So there are some material, looks like material handling things that they're going to want to continue to automate. So it looks like these are pretty heavy parts. And I believe that's kind of an aluminum boron. So this is a stamping operation, the stainless operation. There's a stainless stamping and bending operation that, we're going to see more of. And then this looks like the inner door. Looks like it's an aluminum boron mixture. It's again, I think it's their own custom metallurgy. We'll have to go double click into that a little bit more. But we're basically seeing a stamping operation. And those two gentlemen, I think there's two gentlemen in that clip or a future clip. They basically, the part comes out and they both have to together lift it up and then put it into that rack. Those two people, that will be automated via a robot. A station, a multi-axis robot arm will be able to pull those. And again, those aren't cosmetic. Those aren't, they call them, A surface, but those are not A surface parts. Those are parts where, you can be a little bit more quicker, a little bit less, a little bit more sloppier with the handling, and just get these things racked up, and then they'll move up to the next operation.
Any other questions? Or?
No, I've seen a lot of this. So
Probably
all this stuff
never
looks
this big.
about. No, I haven't seen one this size.
Can we go up and over, Dan?
Yes.
Yeah, let's go up and over.
We can go up and
Yeah,
over. Thanks, Grant.
that will be picked with a robot.
So the panels that you saw, the blanks from the side, will come up here along with other parts, and then they'll move in. Right now it's all forklift. You see all our cherry pickers from construction still here, but they're coming here. We actually have a body shop on the second floor here.
That's
So it's our-
unusual, yeah.
Yeah, well, it turns out those are the least number of parts now. We're down to just over
Yeah.
100.
Yeah.
So moving them up isn't that bad, and they're bigger, so we can get bigger, less trips, and they stack nice, so we get a lot of QPC. So we come in here to mainline, but we're gonna go straight to doors because we're running low on time, just to show you doors from forming to final.
No, to finish.
So kind of zigzag. We're only running one shift right now. Nice
Pause
to
it.
clean up and.
He used a term. He used a QPC, like a quantity per container, quantity per count. Basically, anytime you're moving anything from point A to point B anywhere, it could be between suppliers, it could be within the factory. You're trying to figure out how to get the most amount of material into one movement operation as possible. So he said that as all these parts basically stack really super nicely. These aren't like really like clunky, weird shaped things. So they all stack very nicely. So from a material movement perspective, that to me looks like the piece that they're still working on is the movement between some of the stations. But in terms of the actual steps and the fabrication steps, it looks like all those are automated.
Construction and final debug. So it's kind of quiet here, but Venner and the team were kind enough to stay for you.
Well, that's very
we can
nice.
get
They're
Right.
running one shift. That's the other takeaway. This is one shift. So this is looks like they stayed into the night shift. Just look at the size of the operation too. This thing is massive. Not only X, Y on the floor, but also Z, the height.
So basically, the doors get built this way and go down straight to GA. The main line goes this way and then gets transferred to our powder coat line that does that black coating.
Yeah.
Over there. We kind of have a flow.
But you don't use Elpo, right?
What's that?
Elpo, the stuff that everybody else uses. You dip the whole car in it, basically.
No, I mean, well, this is
you don't need to.
This is it's a soft e-coat with a wet powder just for that black area. So we only have one oven. So we do e-coat it, basically to seal it and cure the sealer. And then we, because the door rings are that boron steel, we need to coat it. So then we put the powder coat on for the aesthetic. We go this way?
Yeah, we go this way.
Door?
Yeah. No, we can go
we'll go
here. I know that this line, bending line, was running dry cycle earlier. I think the other one next to rear door is actually running.
Okay, let's go see the rear one. So we'll talk dry cycle. I'll talk and then you can show them the rear one. So this is our true bender.
Dry cycle is same part
so
over and over. Just
works special on this. This is the air bender I was telling you about. So this is dry cycling right now. We have one of these for each panel. And how it works is, we'll come in here close. You know, currently we're running dry cycles, so you can see any faults and whatnot when we're off. So it'll pick up the panels here from that stack that the guys made in blanking. Picks up a panel, and now it's putting it's about to pick up a fake panel. So it picks up that panel, right? We'll show you the one working over there, and it's going to bring it into the true bend, which is from Trump that we worked with. And this, you can see that brake bend comes down, but that's that air bender. It has that V shape with the air flowing on either side to keep it, you know, floating when we get the mar marks. Flips it around, it'll do the other side, and then once it's done, it takes a good part and puts it back on here, and it'll come out here. So we just wanted to show the dry cycling before we go over and look at the actual part, so you can get the idea of the movements.
That's
now again, we're in the middle of commissioning all our transfers. Usually we do the systems first. So the good parts will come out here. That Kuka base that's missing a robot. Right. We'll pick it up and put it over here, transfer overhead, and go into our door manufacturing cell. So that's it. That's the whole thing that does all the metal for me.
That's a lot simpler than I thought.
Simple is usually better.
Yeah.
We pause it there.
Are we running here?
So one of the things they're trying to do, so that station was dry cycling. They're running probably process capability checks on that robot in terms of repeatability, reproducibility of all the different movements and actions. That V bending thing, I mean, that could be a whole video in itself in terms of them using this high pressure air and why they have to go through all these gymnastics for this for bending the stainless steel is Tesla's using stainless steel in a cosmetic finish on a vehicle on call it an A surface, and that's just totally uncommon. So that's what they developed. Looks like they worked with a company called Trump that they worked with that piece of machinery on, and these are some of the things that I think are going to be pretty difficult to replicate. And the reason they had to do this is really to prevent the orange peeling, the marring and scarring that would happen in a normal bending operation, because again, these aren't normally cosmetic parts. Okay, keep going.
Yeah, this one is running.
Okay. We got front, rear. So this is a rear door?
This is, I believe it's rear door. I mean, this one is able to do both rear and front door.
So this is what you wanted to see. So we get these flat panels in. Now you'll see it actually pull it. Pulls up the flat door blank. And we're running about, what speed do you think we're running at about now? Like 25%?
Yeah, I think so.
Here's the air bender. So the top tool forms on the inner. That actually has no air, and the bottom tool is where we're blowing the high-speed air to float it. You see it makes the one bend? That light flash was a measurement. Make sure it's right on.
Yeah.
If it is, it goes back. It's good. Turns around. Does the other bend. There's two on this side, right?
So do you do any scoring or anything?
Nothing.
On nothing.
Bend radii is 5mm on the inside, right? So it's about 7, 8 on the outside. Anything tighter than that, we started cracking.
Yeah, well, there's a ratio, and that's a ratio that I would have probably guessed.
Because if you go, we tried to go tighter for fronts.
Yeah, well.
But thickness time is, different. Otherwise, we end up with a knife edge in the middle on the front.
Yeah, yeah. Well, the deal is that you work hard in it too. If you do anything less than about 4
times the thickness, yeah. So it comes out. We'll put down the clean part here.
You pause it.
And here we have the.
You heard he said that they were trying to get kind of a tighter radius for front. So that again, when you're Lars and you're in that position, you're trying to please industrial design in terms of how that vehicle looks. Probably Franz himself, as you heard him say, Elon, and then of course he's got to balance off the ductility of that part, the part cracking, orange peeling, in a bending process. So these are all the different things where they've got to strike a balance. I think the other key takeaway is, that was the machine running at 25% efficiency. So this is the whole stage of going through the ramp up process of running those machines at 25%. Different machines are at different stages and different speeds, but eventually what they're going to want to do is they're going to want to sync these stations up. They're going to get enough capacity. If they've got the whole vehicle targeted at a 60-second, I'll make it up, a 60-second click rate, they're going to want to get the output of each station to be running like that. So whatever capacity is needed, whatever speed of the robots are needed. But you can see right now they're running one shift, and they're dry cycling some. They're doing process capability work, and then they're really they're running at that particular part at about 25%. So as they speed this up, that's where a lot of the problems can be found. So there's more excitement ahead, but I would say that they've worked through a big portion, of the known challenges, just running at even 25%.
Robot.
Oh,
not quite ready, but
wow, that base is huge for the size of the robot.
yeah, we can walk around, and outside's a
Well,
good
let's
door.
do that. Yeah.
Hey, thanks for staying late, guys. Appreciate it. So we get the panel out, and this is ready. As I said, right now we're putting them in the racks. Well, they ran out of racks, but you want to put it in a check fixture?
Yeah, you want to put it in
The check
the
fixture,
check?
just so we can look at it.
Sure, great.
This is a go no go clamping gauge, and they're not doing everything through this. They're definitely sampling.
Yeah. So that's it. This is the inner bend. You can see we get a little marring here, but obviously it's B class, right? It's inside. It's maybe gray zone.
What I was concerned about, or what I was thinking about, was just the outside bruising, not the inside.
Yeah.
I don't care about inside.
I mean, you can see on these panels over here. You look on the backside. You can see where you can even see where the air is blown off the dust.
Yeah.
But you come over here, nothing.
Yeah, that's pretty amazing. Actually, you're using two of my favorite, three actually, counting Kuka. They're my
Trump,
go-to.
Kuka, Schuler.
Yeah, if I'm going to do something, I hate screwing around with junk.
Yeah.
And anytime a purchasing agent or one of those engineers with an MBA says, "Well, I got a good price on it," I have an expression.
There's usually
Don't
reasons.
save me any money. I can't afford it, and that's the truth. So
By the way, these are 1.8 millimeters thick.
These are the
yeah,
full real
And
bulletproof.
everything else is 1.4 millimeters thick,
Yeah.
other than the doors.
yeah. Well, you need that extra for the
Well, this
machine
is-
gun. Yeah.
Well, the 1.4 is actually pretty bullet resistant too,
Yeah.
but this is actually takes about 75% of the side crash loads just through the panels itself. And so,
Yeah.
we wanted that extra thickness for the stiffness. So after it goes over conveyance, we'll go into the weld cell, and then we'll finish it. And we'll be
Okay.
done.
Great. So that's one of the things I'm really
just
interested
a
in.
pause there, just a couple more steps, and I mean, you heard a little Sandy talking about in terms of like using really good automation suppliers, really good. I mean, from a couple of those suppliers aren't automation; they're actually process suppliers, like Trump, for example, for lasers, for that bending station, and because what happens in the beginning of a program, very early on, probably a couple of years ago in the case of Cybertruck, is they laid out all their suppliers for automation. They had them come in and they had them quote everything. And so what they did is they built a CapEx budget, using the best in mind, because sometimes the best can get you better process times. And this is the thing, they've got to look at these things. And this is what Tesla does. They know how to do this. I'm not telling them anything they don't know, but this is what companies have to think about, is like, what is the upfront cost of that capital? Because there's always going to be somebody out there with kind of a knockoff that may be pretty good. Eventually there are competitors that emerge, but in the case, he was rattling off Schuler, he was rattling off Kuka, he's rattling off Trump. I mean, those are some of the better suppliers to use in this space, and they've obviously selected them for mass production. So good on them. So just they have to consider all those variables up front. And sometimes what Sandy was saying is like somebody like in a procurement role would say, "Hey, look, I can get you that automation for 20 or 30% off." But then what Sandy's point is you'll be paying for that forever. If they don't have the same process capability, speed, or results. So these are all the factors that have to be considered through the lifespan of building a product.
Mm-hmm.
Okay, we can
How do you
probably motor
fix
through.
that to the
Let's go check it out.
to the rest of the door?
How do we fix it? So we have the inner, you saw from downstairs.
Yeah.
We have the outer. Now we got to put them together.
Right. Without making any mark.
Right, super easy, huh?
All right, piece of cake. Yeah.
So we load the inners in here. Is this running now? This is all off now, right? Maybe?
What's
Looks like
that?
it. You want to check? So see if we can turn it on for you. So basically, we don't have any reinforcements on the exterior panels.
Yeah.
We have a couple of hinge reinforcements just
Right.
locally on the inner. So this cell here takes that inner panel and this hinge reinforcement, it just welds it together. A couple of spot welds, that's it.
Okay.
Pretty traditional.
Yeah, but how do you do it without any marks on any?
Just keep going.
Yeah. Oh. Okay.
Yeah, the line is full right now, so we cannot.
Oh, the line's full, so we can't. Okay. So now we bring the outer in. Okay. Outer comes in here, it gets loaded in here, and we have another laser booth. And the laser booth, because the exterior surface was the most critical, right? We didn't want to get any burn through, mark through, see
Right.
through.
Yeah.
So
You don't want a blue mark either.
So the tolerances have to be basically micron level precision.
Yeah.
In order to get the two together. Do you have the one part here? There?
Yeah, we got a part here.
Yeah. So this is all closed up laser, but you can see the line's full here, so that's why it's not moving. We can come in here, it's fine. So this is a part as it comes out, and you can see the laser welds coming here. So we actually clamp down on all the corners, and the laser welds go all the way around the perimeter. And what that does, I should really...
I already got it now. I didn't think of that.
So it comes around the perimeter. It actually bends this in just ever so slightly, gives it a little roundness. Helps
Right.
with the A-surface light coming off the side, so you aren't edge to edge, you got a little tip. But you don't get it, we had to work, I don't know, for months on the current and the heat that's going in, so we don't get burned through with tolerance and
Right.
whatnot.
Yeah.
Trail off. But that's it, it's that simple, and we're done. But now you'll see, like, we do have some burn marks here. What we do is we go into laser ablation, and we're just gonna go
Right.
clean it all up.
And that's what I thought maybe you were going to do with the outside of this thing. So I noticed you got two
Pause it for a
vibration
second.
Yeah, it's
patches.
just big.
So they talked about two different things, Herbert. One was how do they get to the point where you can process this at a pretty high yield without any where you're laser welding the outer to the inner door. And what Lars basically said, it was what they figured out what strength they need, and they just started backing off until they can minimize it. And there's still probably some residual issues. They wouldn't get into the yield. But then he says there's another post-processing step, that laser ablation step. So I would think that step is in there right now as a crutch, and it may stay there permanently. We'll see. But I'm assuming their goal, in Tesla, is to figure out how to get that bonding process between the inner and the outer to where there are no marks, and you don't have to go. The fewer amount of material that has to go to that cleanup step, obviously, the better it is. But that's what they're using. Basically, an ablation process is removing material. So looks like they've got another step it's going through, and they may have a physical. We'll see. They may have like a physical brush that they're moving the part through as well. So let's continue playing it.
Big oil can, right?
Yeah.
Just a little damper.
And that's another thing that was going to be a question, but now it isn't. Okay.
So we come out of laser weld, we go into a holding cell because we have a buffer, basically just a buffer.
Yeah.
And then we come over here to finishing. So all these lines are integrated together by Bernard's team and the guys, because actually every station, you can even see with the robots here, finishing station has KUKA, welding station has Fanuc. They're actually from different companies because we like to spread it out to people that are good at what they do, right? And so then we come in here to finishing. You want to explain how finishing works a little bit, or?
Yeah, sure. So from welding, we drop it in our handover stand there. Robots will pick it up, drop it in a stand, and we got robots on the other side. They have like a buffing pad.
You see on the bottom of that head that's like inside the shape here, you see it's two Brillo pads basically.
Yeah.
Hanging down there. Actually three, right? Three across.
Yeah, I see it.
And all that does is very lightly goes across, back and forth.
Yeah, it does a couple of runs over the complete door, and then they use a different type of pad for the other robot, and then this is a completed part after finishing.
This is what it looks like, done and done. And then that final cell in the closed door, that's where we ablate
do the laser ablation.
Yeah, so you can see kind of on this one actually, locally these spots. We just go, pss, 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 and we get this one's not ablated, that one's ablated. We only ablate
The ones that are exposed.
visible.
Yeah. Cool.
You can see these one better.
Yeah, this one is pretty visible. Yeah.
So you can see the fish bowls, and we do the same thing on the laser weld just to clean it up.
Yeah.
But these are all exposed in the end. There's no paint, there's nothing. That's what we got.
Yeah. Marvelous.
So right now these get racked and then brought down to general assembly, but eventually they'll just flow straight down through an elevator. So this whole process runs at a cycle time about 40 seconds when we're at full speed. And we could go faster, but it's
40
just,
seconds.
Yeah. 40,
Well,
80 seconds.
because I was going to say 60
that's
seconds
for a
is
line,
normal.
but yeah. I mean, this one is about 60.
Yeah,
50 something.
60 something would be about what I would guess. Yeah. So you really don't, because when I went through this factory the
Y.
first time for the Model Y, that's running at 42 seconds.
Yeah, that's why I meant
And
the
the same
model.
thing as the what do you call it? Berlin factory, 42 seconds.
This one's a little slower, just on
Pause
volume. You know.
No,
That's one. If Elon were to be watching this video, I know the other gentlemen that were off camera there wanted to make sure that Lars got it right in terms of where they're at from a processing speed, because if they signed up for something on that video, I could see a fun-loving CEO that would want to force them into those process times and said, well, you said it, so figure it out. So yeah, no. So I think the key here is like, this is kind of the end of the, stainless parts process. There's other parts we didn't see get processed. Obviously the rear of the trailer, the rear of the door hinge and so forth. There's many other parts, but basically these things now are built up into a sub-assembly state, and then they get moved to an area called general assembly. And that's where, Tom Zhu and his team, get the entire vehicle and get everything put together. And Lars is still obviously accountable from an engineering perspective over all of that as well. But, this is basically getting everything. You saw raw sheets, stock coming in and having it cut, formed, and then bonded into sub-assemblies, cleaned up. So it's a perfect looking piece. And then those all are moved to the general assembly area of the building. So fascinating for me to see the size of the operation, to see kind of the XY, floor plan and how things are laid out, to see the suppliers that they're using. Everything, there's a lot of multi-sourcing where they can multi-source, especially on the multi-axis robots, Kuka and Fanuc, and it looks like they're well on their way. And then they'll staff the second shift, and they'll staff, they'll still have this operation eventually, I'm assuming at some point, running on the order of 20 to 22 hours a day, and leaving, a couple of hours for maintenance and changeover time. And that will be a fully running operation, I would imagine, when they're able to get that next shift up and trained.
What a treat for us to watch this production line, the beautiful factory, the beautiful automated robots. Lars, so smart. He knows everything about what's going on. He kept up with Sandy. Sandy can keep up with him. And they just shared everything. They just walked in that new video, and he explained every little detail. There's no concern for competition, but it looks like that's very confident. Cybertruck production is, hitting the micron efficiency, and they're just going to be able to, improve this bit here and that bit there, add another a robot here, and things are going to move faster.
Yeah, what would be fascinating for me, given my experience, would be to see us, now to be on the other end, the receiving end in the general assembly area, and all these parts come in, and let's see how everything fits together and how the yields of those are. Because what you would want to optimize for is, when you're ramping, you would want to localize any kind of process process variation. You want to get it down to the smallest part possible at the earliest point in the factory possible. That's the key that they're trying to do right now. So they're feeding this material at low speeds all the way through. It's getting all the way through to general assembly. And if anything gets kicked out at general assembly, then they're walking that all the way over back to that point of origin and trying to figure out how to phase contain that defect in the area that it was created, or they have to adjust the tolerances on a particular machine and then crank it down further. So this is why you start at low speeds and then you slowly crank it up. But I was glad to see all the production capacity there. Yes, there's certain movement robots that are still needed to move material from point A to point B. But in terms of the actual automation that's doing the fabricating piece and all the assembly piece, all of that looks like it's there. And that was very encouraging to see.
Well, that was a real pleasure, a real treat. Thank you so much, Jeff. And your expertise in manufacturing is so critical. You help explain a lot of things. You added a lot of color to it. Appreciate you. Really lucky we had you here. Talk to you soon. Follow Jeff.
Yeah, Sandy did a great job. Lars did sorry, I was just say Sandy did a great job. Him and his team, the video team, and Sandy kind of narrating. He does a great job. He kind of knows the right questions to ask. And Lars, of course, like you said, he was very well prepared. Him and the production managers and the technical managers that were by his side were very well prepared. So this is a team that knows what they're doing. And just they know what the endpoint looks like, and they're on their way getting there is my takeaway.
Exactly. Thank you, guys. Bye-bye. I've created a website that is the most comprehensive resource for the Tesla investor. Please check it out. Simply go to my website at herbertong.com.